I joined Google is because of a startup company called GraphicsFuzz that I founded from my research at Imperial College London, founded it in 2017, and the company was acquired by Google in 2018, hence me joining Google nearly full-time and retaining a part-time position at Imperial College. So what I'm going to do in this presentation is tell you a bit about the GraphicsFuzz project, give you a flavor of the research that underpins it, and tell you some of the directions we're taking it in right now. So GraphicsFuzz is about doing automated testing of graphics drivers, and in particular, the compilers inside graphics drivers that make programs called shaders run across the parallel processing units of a graphics chip, a GPU. So suppose you're a game developer and you write a little program that's meant to produce some visual effect like this pretty picture here, but you run it and you instead get something malformed like this effect here. That wouldn't be great, and this can happen because of a wrong code compiler bug, where the compiler has silently miscompiled your little program so that it doesn't crash, but it produces the wrong result. So that could be pretty bad. Probably worse for a game developer, less interesting from an academic perspective, but worse in practice would be if you're meant to have some nice visual effect, but instead your system crashes. And as I'm sure you know, device drivers are very close to the operating system, and problems in device drivers can often be the cause of machine reboots, device reboots, blue screens of death, etc. And these days, 3D graphics are deployed in web browsers. There's a technology called WebGL, which is supported by all major web browsers, where a web page can invoke the OpenGL ES API and have things run on your GPU just by you visiting a web page, unless you've disabled WebGL, which most people haven't. So you might want to play some game that had some nice visual effects, but it might be that actually the page you visited is a malicious page that can exploit a shader compiler bug to capture images being rendered in other tabs of your browsers and get some maybe malformed version of those images and send them off to a remote server for capture. This is an example that we found with our research where we were able to capture any web page in another tab. Obviously we chose a banking web page, just fun when we demoed it. And this was due to a bug where one GPU process would crash but not actually be properly killed, and then it would be able to capture data from another tab that was being shared. Okay. So, as I mentioned, the GraphicsFuzz project is about finding bugs in graphics drivers, or more specifically, shader compilers, which are the largest components of any graphics driver. And we use a technique called metamorphic testing that I'll tell you a bit about during this presentation. So what's a shader? I'm going to use that word a lot of times in the talk, so let me say once again what it is. It's a program that runs across the GPU hardware to perform a custom computation. If you're not familiar with graphic shaders, maybe you're familiar with kernels from CUDA or OpenCL, and a shader is basically the same as a kernel, but in proper graphics we call them shaders. And there are two programming models for graphics that I'm going to talk about during the presentation. One is OpenGL ES. OpenGL is Open Graphics Language, and ES is the embedded subset, and Vulkan, which is a more modern graphics programming model. And each of these programming models has its own shading language. There's a language called GLSL, which is the OpenGL shading language. And there's a language called SpearV, which is the Vulkan shading language. So those are the shading languages we've been targeting in our work. So what is metamorphic testing? Well, rather than give you an overview of metamorphic testing in general, I'm going to explain what metamorphic testing is in the context of compilers. It's a pretty simple idea. Let's say we've got a program P, and let's just assume that the program P is a deterministic program, and that it's also free from undefined behavior. So we're not going to have any concurrency if that concurrency would cause non-determinism, and we're not going to have any, say, null dereferences or out-of-bounds reads if it's a C program. If we compile the program into an executable and run the executable on some input, we get some output. And the thing that makes compilers really hard to test is that we don't have any way of knowing a priori what the expected output should be when we run the program on that input. Knowing that is as hard as building a compiler. And for a complex language like C++, for instance, that's really difficult. But if we can apply a semantics preserving transformation to the program P, do something to the program that makes it look very different to the compiler, but in a manner that doesn't change what it ultimately computes, then we can compile that program P prime, and we can run the resulting executable on the same input to get an output O prime. And because the transformation was semantics preserving and the program is deterministic and free from undefined behaviors, these outputs should match. If they don't match, then there's a bug in the compiler. Or there's a bug in the transformation that claimed to be semantics preserving, okay? Or the program wasn't really deterministic. But assuming that the transformation is good and that the program is good, then there must be a bug in the compiler, or in principle in the hardware. So if you're familiar with metamorphic testing, then the metamorphic relation here is that the function compile and execute applied to a program P is equal to compile and execute applied to the semantically equivalent program P prime. And there was a really nice paper in PLDI 2014 that inspired me to get involved in research in this area called Compiler Validation by Equivalence Modulo Inputs Testing. And this isn't advertised explicitly as metamorphic testing, but I believe it is an example of metamorphic testing. And the idea of this work was take a well-defined program P, compile it, and profile its execution on some input. And if the program is well defined, then that profiling is going to partition the statements of the program into two disjoint sets. The statements that do get covered when you execute the program on the input I, and the statements that don't get covered. And if you run the program again and again on the same input, you'll get exactly the same partition if the program is deterministic and well defined. So if we call the statements that are not covered by I D for dead, so they're not globally dead, they're dead with respect to I can't reach them. We can then do something quite neat, which is from the program P, we can make a whole load of programs, P1, P2, P3, P4, as many as we wish, by messing around with D. We could, for example, delete some statements from D, or inject some new code there, or apply some mutation operators to the statements in D. And if we compile all those programs and run them all on the same input I, they should all yield the same result, because I doesn't touch D, so changing D should not affect the results on I. And if we find a case where we get a different result, then almost certainly the compiler has miscompiled that variant, in this example P2. Of course, theoretically, that could be the only one it's correctly compiled, but in practice, it will have miscompiled that one and correctly compiled all the others. Okay, so mismatches here indicate bugs. And this technique was really successfully applied to GCC and LLVM. And the developers of this EMI technique were acknowledged in the LLVM 4 release notes for having reported many, many bugs that got fixed. So what we're doing in GraphicsFuzz is something very similar to this, except rather than profiling to find unreachable code, we're just generalizing the approach to apply semantics preserving transformations in general. And this was motivated by the fact that it's not very easy to do code coverage for GPU shaders. That's not very easy to do. And secondly, if you take existing graphics workloads, they probably don't contain all that much code that's reachable for some inputs but not others, because that's not typically how you program GPUs. You can have conditional code, of course, but you don't tend to have loads of it, because you would probably split your code into different shaders in that case. So we wanted to try and apply this technique to graphics compilers, but rather than try to replicate the technique exactly, we had the idea of, instead of trying to do this profiling approach, we would do our own semantics preserving transformations. So we take an original shader, we produce a pile of variants by doing semantics preserving transformations that we have implemented in a custom program analysis framework. And then we get a pile of images out when we push these things through the GPU driver and run them on the GPU. And the images should all be the same. And if they're not the same, or if there's a crash, then we know there must be a bug in the graphics driver, probably in the shader compiler. And of course, in principle, it could be a bug in the GPU hardware itself. So it's an example of metamorphic testing for graphics drivers. Question is it useful? So we apply these transformations repeatedly to a shader to blow it up into a very big equivalent shader. That big equivalent shader yields a different image when you use it for rendering. And then I say to someone, trust me, there's a bug in your GPU compiler, good luck fixing it. Well, this is not going to work very well. First of all, they probably won't believe me that this horrible looking program is equivalent to the original program. Why should they? There are plenty of bugs in GraphicsFuzz. Second, they wouldn't really have a clue where to start debugging this if this program is hundreds of thousands of lines of code when their original shader was maybe 100 lines of code. So what we've also implemented is a test case reducer that it follows a delta debugging style of reduction with the twist that rather than arbitrarily reducing the shader that produces a bug, we reduce it by reversing the transformations we applied to it so that we preserve semantics of the shader always. So what we do is, while there's an image difference or a crash, we randomly remove some transformations, and we keep doing this while the bug persists and we don't find more stuff to remove, or we reach a resource limit. And what we end up with is a small difference from the original shader that isolates the bug in the graphics driver. So for example, we might have a diff where what we've done is we've added in this if statement. If the frag coordinate, if its x coordinate, is less than -100, which is impossible, then return. So that's a semantics preserving transformation. We're adding a piece of code that's not reachable, that shouldn't have an effect on rendering. So if that completely changes the image you get rendered, then you know there must be a bug in the shader compiler. And if you're the developer of the shader compiler, it's probably pretty easy to start debugging that bug because you've got this diff to guide you. Whereas if you had the original transform shader, where we'd applied many, many, many transformations, you wouldn't have had a clue where to start. But we want to apply loads of transformations randomly because we don't know in advance where the bugs are going to be. So we apply loads of them, find a problem, and then shrink down to the minimal subset that trigger the bug that can be used for debugging. Does that make sense? Yeah, please.
I'm just curious, how smart are you about removing all those transformations to get to the minimal diff and the minimal test case? Is there some real smarts in it, or it's sort of random or brute force or
well, we have a set of reduction rules, and we have a guarantee that if you wait long enough, you will eventually reach what's called one minimality, where no rule is capable of making the shader smaller and preserving the bug. However, the rules we have may not be enough to find the smallest shader that exists that triggers the bug.
There may be multiple paths.
Oh yeah, there are many, many paths. So there may be many one minimal shaders that may not be all of the same size.
Looking for some of them or just for one?
We're looking for one. Yeah, and the idea is that you use this, you fix the bug, you run the fuzzer again, you fix the bug, you run the fuzzer again. Yeah. Any other questions at this point? Very happy to take them during the talk. In fact, I would prefer to. So please do interrupt if you have questions during. Okay, so if we actually trigger a crash in the shader compiler, then we don't need to preserve semantics. We just need to preserve validity. So our reducer is much more aggressive in the case of a crash bug. It actually is more like delta debugging. It does validity preserving, but not semantics preserving reductions to the shader to find the smallest thing we can that triggers a crash. So this is a nice little shader that doesn't render anything. It just calls the power function on some vectors, and this crashed a compiler of an Android graphics driver. And that's a really nice thing to add to a regression test suite. And what we were doing before we joined Google was running this comparatively on many devices. So this is deliberately too small to read, but each row is a different device that we had and we were able to run some shaders on. And each column, the leftmost column is the reference shader, and each other column is a variant shader that we randomly made from that reference. And what you should see is this flag everywhere. But what you can see instead is, well, there's a really interesting row there where you can see some garbage images that have been rendered. You can see bits of the right rendering coming through, but some nasty wrong results too. And many that have text in, these are crashes or link errors or compile errors. And you can probably see that some of the commonality means we're using devices that have got drivers from the same vendor in them. And we were able to run this on many shader families to find many, many bugs. And a really nice thing about this metamorphic testing is that the tool tests itself, right? So you might wonder who fuzzes the fuzzers. Well, actually, GraphicsFuzz tests itself in a sense. So suppose that we've got, and this is just made up, this slide is, the results are made up, but let's say we've got an ARM GPU, an Intel GPU, an NVIDIA GPU, and a Qualcomm GPU. So these all have different drivers. They may share LLVM inside them somewhere, but they're basically different drivers. If we find that we generate a shader that magically causes them all to miscompile, that almost certainly means, well, it always means that there's actually a bug in GraphicsFuzz, and we've done a transformation that's not semantics preserving. So then we pick one of them, we do test case reduction, and we get a minimal diff. And the minimal diff, we can see, oh, that's not semantics preserving, and that lets us debug our own tool. So I think that's kind of cool that fuzzers fuzz themselves. So what are we doing with Google? Well, mobile gaming is increasingly in demand, and mobile graphics drivers therefore need to be reliable enough to run interesting games and interesting content. And I mentioned before there are these two main graphics APIs in the Android world, OpenGLES and Vulkan. And OpenGLES, although it's very widely used, it's somewhat legacy, and Vulkan is where we would like the future to be. So we are trying to make Vulkan as reliable as possible using GraphicsFuzz. But the problem is that GraphicsFuzz doesn't work for Vulkan. It works for OpenGLES. So what we're doing is we're testing Vulkan via translation, via cross-compilation. We take an OpenGLES reference shader, And we use GraphicsFuzz to make a variant shader by applying a ton of these transformations. And then we push both of them through this front end called GL-Slang, which is able to compile GLSL, the OpenGL shading language, into SPIR-V, the Vulkan shading language. And then we can push these through a Vulkan pipeline and compare results. So from our by fuzzing at the OpenGL level, we're able to find bugs at the Vulkan level via cross-compilation. A clear limitation is that the cross-compiler produces idiomatic code, and we're not going to produce tests that don't conform to those idioms because everything's going through that cross-compiler. So as I'll mention later, we're now building some Vulkan-first tooling, but we've been able to go a long way by using this cross-compilation approach, and we've also been able to find bugs in GL-Slang in the process too. And then what do we do with these bugs? Well, Android has something called CTS, the Compatibility Test Suite. And every year there's another Android dessert release going alphabetically through the alphabet. Marshmallow, Nougat, Oreo, Pie, and Q will be announced soon. I don't know what it is. And an OEM, an original equipment manufacturer, like Samsung or LG or Google themselves with the Pixel line of phones, what they've got to do is, if they want to be certified as Android Q, for example, they've got to pass the Compatibility Test Suite for Q. And new, more rigorous tests can be added to the Compatibility Test Suite for the next dessert release. They can't be added to previous dessert releases, but they can be added to future dessert releases. So what we're doing with GraphicsFuzz is we're finding problems, and we are adding compatibility tests for them for future dessert releases to raise the quality bar for graphics, to make it harder, I guess, to build a correct graphics driver, or not harder to build a correct graphics driver, as hard, but harder to build a graphics driver that's deemed correct. So we're raising the bar to be recognized as correct. Another thing we're doing is we're using metamorphic testing to find vulnerabilities. The Chrome web browser, also from Google, has a very large number of users, so there are lots of people trying to attack it. And there's a really great project from Google called ClusterFuzz, which is a continuous fuzzing effort for Chrome. All the time, there are many, many bots running tests on Chrome using libfuzzer, which is an LLVM fuzzing framework. And Chrome is compiled with a bunch of sanitizer tools, like address sanitizer and thread sanitizer. And these sanitizers find security vulnerabilities in the browser, thanks to the use of libfuzzer. So we have a project where we've teamed up with people from the Chrome security team to, instead of using libfuzzer, we're using GraphicsFuzz to fuzz WebGL shaders and run them through Chrome. And this has been successful in finding quite a lot of vulnerabilities in WebGL support, despite the fact that the Chrome security team don't care about preserving semantics. They don't care about wrong images. What I mean is, they'd love it if WebGL produced nice images all the time, but their primary concern is, are there exploitable vulnerabilities? So they're primarily concerned with looking for things like buffer overflows. So our semantics preserving fuzzer might not seem to be the best fit for that job. So what I find quite interesting to think about is why we've actually managed to find a lot of vulnerabilities in WebGL support in Chrome via this metamorphic testing approach. And I think it's for the following reason. If you think about mutation-based fuzzing, like American Fuzzy Lop, where you take an input and you mutate it in a rather arbitrary way by messing around with the bits of the input, typically you have an original test input that goes deep through the layers of a system. In this case, a shader compiler. It's got a parser, a type checker, an optimizer, a code generator. You mutate the test, and it's probably not going to make it through the parser. You mutate it again, and it probably won't make it through the parser, right? Some of these bugs that, some of the inputs that go in the parser will find vulnerabilities in the parser, which is fantastic, because that's the first place you would attack. But very few inputs are going to make it past the parser, and almost none are going to make it all the way through the whole system. Some will, but very few. If you think about metamorphic testing, because we do this semantics preserving thing, all of the inputs are valid, so they all make it all the way through the shader compiler, unless they crash the shader compiler. And along the way, they can trigger buffer overflows that address sanitizer can find, for example. So by being validity preserving, which is a superset of semantics preserving, we're able to find vulnerabilities deep in WebGL support in Chrome that you don't find using mutation-based fuzzing with libfuzzer. What we don't find are interesting vulnerabilities due to malformed inputs, so the techniques are complementary. So it might be interesting to look at doing non-semantics preserving but validity preserving fuzzing here as well. So yeah, we find deep vulnerabilities, but we don't find bugs triggered by malformed inputs. And here's an example of a GraphicsFuzz ClusterFuzz WebGL vulnerability. So you can see here a heap buffer overflow has been triggered by, and there's a stack trace for you here. The next thing I want to talk about is the use of metamorphic testing for an ecosystem of tools. So because we produce valid inputs, so from an original shader we produce other valid shaders, we can actually test whole layers of tools, not just one shader compiler, but a whole layer of tools that work together. So I want to tell you a bit about the adventures a graphics shader can have through the ecosystem of tools in the graphics world. If you take an OpenGL shader, it's a GLSL shader, you can run it on a GLES driver. So you can run it on your Android phone or your iPhone. You can also run it on Swift Shader, which is a software renderer for folks who don't have enough money to have a decent GPU. Swift Shader can still give them some graphics rendering support. Or for folks who are using a blacklisted driver, they can still get WebGL in Chrome, for example, because of Swift Shader. You can also, as I mentioned, cross-compile GLSL into SpearV. You can then run that on a Vulkan driver instead of GLES, and you can run it through the Vulkan version of Swift Shader. HLSL is Microsoft's shading language that's used for most AAA games, and there's a compiler called DXC that has got a SpearV backend. So that might not seem relevant for our GLSL shader, but not yet. Then there's a tool called SpearV Opt that's an optimizer at the SpearV level, so it's a kind of shader compiler. Then there are other shading language stacks like Apple's Metal and Microsoft DirectX. But then there are tools that translate from GLSL into some of these shading languages. So for example, Angle goes from GLSL to HLSL, which is how WebGL is implemented on Windows. So all of these tools are in some sense shader compilers, or they're shader transformation tools. They all have the potential to have shader compiler bugs lurking inside them. And we can actually do testing of loads of them using GraphicsFuzz at the GLSL level by mutating at that level and then pushing the shader through this toolchain. So this has been a really good way of giving this whole ecosystem a workout. A problem, of course, is how do you know where the bug is? If you get a crash, that's fine, you know which component crashed. But if you get a bad image, it can be genuinely pretty difficult to know whether the bad image is because of a bug in GL-Slang's conversion to SpearV, a bug in SpearV Opt going back to SpearV, a bug in a downstream Vulkan driver. That can be difficult. But you can eventually figure it out and get these bugs fixed. What we're working on now is SpearVFuzz, which is a direct fuzzer for Vulkan. And there's not too much to say about this at a top level other than it will take SpearV inputs directly. So it won't be limited to inputs that came via the GLSL route, so we can do some more SpearV specific things. But for me, something that's very fun about working at Google compared with academia is that it's fine just to rebuild another fuzzer that essentially is the same if it will be useful. We don't need to write a grant proposal about it and say why it's going to be fundamentally different and why it's going to be earth-shatteringly new. It just needs to be useful, and I'm sure it will be useful because there will be many bugs related to SpearV compilation that we can't trigger via this GLSL route. And another wonderful thing is, just from an engineering point of view, we get to not make a ton of mistakes we made when building GraphicsFuzz that we couldn't have foreseen when we built GraphicsFuzz. But now building SpearVFuzz, we can do things in a cleaner way. Of course, we'll make new mistakes, but we can at least not make those mistakes again. So that's really good fun. And we're also working on something called GraphicsFuzz Auto, which is a little bit like ClusterFuzz for graphics. It just continuously generates a shader, runs it, reduces it if it finds a bug, deduplicates it to see whether it's a known bug, and if it's a new bug, automatically generates a patch for the compatibility test suite, so that with a little bit of manual review, that patch can be added. So we can really crank the handle and get as many tests exposing bugs into the compatibility test suite as possible, so that hopefully we put ourselves out of business and can't find any more shader compiler bugs because they've all gone away. Maybe one day that will be a reality and I'll have to find a new project to work on. Okay, so those are the main things I wanted to talk to you about. In summary, GraphicsFuzz is a metamorphic testing technique for shader compilers. And if you are interested in doing any kind of compiler development work, then I hope you'll consider metamorphic testing as a good approach for testing your compiler. It avoids the Oracle problem by producing equivalent programs that when you compile them should give equivalent results. And that's actually very powerful. We're finding bugs in Android Vulkan drivers mainly by cross-compilation. So we're working at the GLSL level and cross-compiling to SpearV to find bugs in tools that work on SpearV. And surprisingly, despite the fact that you don't need to be semantics preserving to find vulnerabilities, it seems that being semantics preserving lets you go deep through a system because you don't get rejected by the front end, allowing you to find deep vulnerabilities. So combining GraphicsFuzz with ClusterFuzz has been good from that angle. And in the future, as well as direct fuzzing for Vulkan and better test automation, we also want to start working on fuzzing game traces. So capturing traces from games and then replacing the shaders with equivalent shaders to try to expose crashes that are sort of close to affecting important game content. At the moment, we're running things on handwritten shaders that we found to be good at exposing bugs, but what we want to be doing is capturing shaders from games and using those as the seeds for our fuzzing efforts. Okay, thanks for listening, and I'd be delighted to take any questions you might have.
Thanks, I enjoyed that talk. I guess one of the measure of the effectiveness of any approach like this is, as I understand it, you take the original program, you transform it to give you an equivalent, and then you try and reduce it.
Yeah.
So what is the overhead in terms of code size between the original and the reduced version of your transformed shader? I mean, how much extra code is the compiler guys going to have to go through to try and, I know it's a difficult question.
You mean how big is the delta from the original shader and the minimized transformed shader?
Exactly so.
Yeah, it varies. It's typically very small, usually a few lines of code.
Okay.
Sometimes it can be huge, and that often indicates a resource-related bug, like maybe some bug that only occurs when the compiler consumes a lot of memory. And those ones are kind of impossible to shrink down because the reducer can try almost anything at once, and once the shader gets below a certain size, the bug disappears. So yeah, those ones are maybe less interesting. But yeah, when there's a plain miscompilation bug, typically a very small mutation can expose it. Just in the way that when you come across a compiler bug when you're developing, you can usually work around the compiler bug by making a semantics preserving transformation of your own. Game developers do this all the time.
Really cool stuff. I was wondering, so you compare images, right, on a pixel level, I guess, to find out if the shader did something different.
Did you say, do we compare pixel level, or we don't?
Well, I assume you do, like you compare the image, or...
Yeah. What we do, we don't compare the image pixel by pixel, because the OpenGL shading language is very generous when it comes to floating point. So it has a lovely statement about how small differences are okay. And small differances doesn't have a meaning, and when the small difference is inside a loop, that has even less of a meaning. Right. So what we do is we use two things. We use the chi-squared distance between image histograms, and if the difference is below a certain threshold, then we flag, above a certain threshold, we flag up for review. And we also have our own thing called fuzzy diff that we've kind of written in a custom fashion based on experience. But that's a hard problem, actually, really automatically deciding when an image is bad enough.
So do you rely on the shaders being deterministic? Like if
you rely on the shader being relatively numerically stable. So if you have a shader that has, there are some really nice shaders on ShaderToy that compute fractal trees, and they're very, very sensitive to floating point.
But like for example, if you had like a shader that did some Perlin noise stuff, that's based on random values, like
then that input would need to be fixed. Yeah, the shader needs to be deterministic, otherwise the image, there's no way to distinguish between a compiler bug and just a different input.
Yep.
Simon.
So when you talked about the requirement that the algorithm should be deterministic, I was thinking that maybe you could have a deterministic algorithm and still have different acceptable outputs. Like, you know, the run depends on the available memory, and if you make the program a lot bigger, it might run with a slightly different approach to get the results more quickly, or whatever. Don't you have that issue that deterministic algorithms may still have more than one legal output?
Well, I would say if an algorithm on a given input can produce multiple outputs on different runs, then it's not deterministic. Of course, sorting an array can produce many different permutations if the array's got duplicate elements. But if your comparison then can distinguish that, then that would be a problem. Right? But the nice thing about the metamorphic testing approach is that to some extent that problem goes away, because if you've got a shader that implements an algorithm, if you do semantics preserving transformations to that shader, it will not change the way the algorithm is implemented, right? The same results will be computed.
Isn't the size of the program also an input?
Say again?
Isn't the size of the program also an input?
An input to the program? I guess if the program would be able to inspect itself, then it could be. but graphic shaders can't.
If it decides what to do based on how much memory is left.
Yeah, so the program so the program would need to be, well, the transformations need to be semantics preserving with respect to the program, so they wouldn't be in that case, if that makes sense. Yeah. So it's just you just have to pick the right programs. You know, your programs need to be constrained enough for the technique to work. That issue you mentioned, I don't think it's possible in the graphics world to reflect on the size of the program and do different things. But if it were, you wouldn't be able to use those programs, right? Or you'd have to have transformations that didn't change the size of the program.
Right. So you mentioned that about on the slide about chaining from through angle to get from GLSL to HLSL, and then through the DirectX API and so on and so forth, and know where a bug can pop up. Have you considered something equivalent to git bisect, as in do a binary search on trying to find where exactly the bug in the pipeline is?
I don't think it would work. Because let's say you're interested in finding bugs in Apple's implementation of Metal. Let's say you're doing that by using Molten VK, which is an implementation of Vulkan on top of Metal. And let's say you're then fuzzing Molten VK by using a GLSL shader and pushing it through GL Slang. So you're going GLSL to SpearV via GL Slang, and then SpearV to Metal via SpearV Cross, and then you're running that on Apple's driver. Ultimately, you get a bad image out. How do you remove one of those components? There's no way of saying, right, let's disable SpearV Cross. Now you can't get from SpearV to Metal.
Well, what I'm saying is, if you manage to have, a fuzzer for, Metal, a fuzzer for Vulkan, a fuzzer for GLSL, a fuzzer for HLSL, then I think you'd be able to do this sort of bisection.
But I think if you had a fuzzer for Metal, you could just use that, and then you wouldn't. If you had a fuzzer for Metal, you could just test the Metal driver directly, and then you'd find a bug in the Metal driver. So I was simply making the point that you can avoid needing to build a fuzzer for Metal to some degree by fuzzing up at this level and using all this chain of tools, but the price you pay for that is two things. One, the code you end up hitting the Metal driver with will be idiomatic based on what these transformers do, and two, you won't know whether there's a bug in the Metal driver versus a bug in one of the components that got you there. Of course, a way around it is to build a Metal fuzzer, but let's say you didn't want to do that. You could already find bugs in a Metal driver using GraphicsFuzz currently. Make sense?
Hi, I'm curious about what kinds of semantics preserving transformations you did, and did you have to be creative in how you designed these things to find the bugs?
Yeah, thanks for the question. We have had to be creative in how we design them. There's not really any particular science to it. We've just thought of things that we either think would be easy to implement, easy enough to implement we should just try it, or that we've got a reason to believe might be effective at triggering bugs. So in the latter category, I know just from experience that GPU compilers are not typically that well tested with respect to complicated control flow. So for example, a transformation we do is we take a piece of code and we wrap it in a do-while loop, and we make the condition of the do-while loop false. But we don't use literally false, we use a generated expression that is guaranteed to evaluate to false, either because it's complicated or because it depends on a runtime condition that we will, at runtime, inject such that that guard evaluates to false. And then the reducer will try removing that loop completely, and if that doesn't work, if the bug goes away, it will then try simplifying the false until sometimes you can actually simplify it to literally false, sometimes it can be a much simpler version of the complicated false we had there. So that's one example. Another thing is taking a random selection of scalars using the shader and packing them into a vector, and then whenever you would have accessed the scalar, access the relevant component of the vector. So that's semantics preserving, but gives the compilation of vectors more of a workout than otherwise would.
Strategies as you went along, and
as we've learned more about graphic shading, as we've thought of new strategies. We haven't done any work on trying to, for example, infer automatically new strategies. That would be like the next big grant if we weren't allowed to just go and build the next tool. And I think it would be a really hard thing to do as well.
So I'm no shader expert, so I don't know if this is possible, but do you test different views of a scene? Because both the vertex and the fragment shaders ultimately depend on how you view the scene. So I guess you could have a case where if you view the scene from a different angle, you could have a bug manifest, whereas you couldn't in some other cases.
So when you render a shader, you have a bunch of pipeline state that actually controls the angle that you're viewing things from, and also controls a bunch of inputs that are usually called uniforms that are used inside the shader. So what we do is we fix those and we supply them to the fuzzer in a JSON file, so it knows this shader is going to be run with these uniforms. So the compiler doesn't know that, but the fuzzer, when it makes the variance, does. So that means that we can exploit known values of those uniforms when we do transformations. I mentioned about obfuscating the value false, for example. What if we know that this uniform is set to 7 and that uniform is set to 32? We can make false by saying that this one is greater than that one, for instance. Okay, I think we're done. Thank you very much for your attention. Cheers.